Guys, welcome to my YouTube channel. Today I'm going to discuss the electronic configuration, and for electronic configurations there's a need to actually talk about the orbitals. I don't want to talk about the orbital shape. I'll just quickly go over to the types of orbitals that we have, and then we will move on to our electronic configuration. So the electronic configuration is in its essence a way that we do add electrons in the atomic orbitals. Atomic orbitals are places where electrons actually orbit the nucleus, and it's in a layered fashion. So we have layer 1 through layer 7. That's why in periodic table we have period 1 all the way to period 7. Okay, also these two are period 6 and 7 here, but we just show them below because we don't have enough space on our periodic table. And these layers that we're going to talk about are also different types of orbitals depending on their shape. I won't talk about their shape today, but I will talk about the number of electrons that each orbital can host, and then we will go on and on trying to do electronic configuration. When we write down how electrons, like for example Ni nickel here has 28 protons, so it also has to have 28 electrons. Electronic configuration means to write down exactly how these 28 electrons are put into different layers and different orbitals in its configuration. This is called electronic configuration. Okay, so there are four types of orbitals, and these orbitals we call them sublevels because each layer, as I just told you, each period in the periodic table, each layer or each period has its own kind of sublevels or orbitals that we will talk and see. So the first type is an s orbital. It only occupies a maximum of 2 electrons. The second type is p orbital. It occupies maximum of 6. D is another type of, or the third form of orbitals. It occupies 10. And F is the fourth type of orbitals. It occupies 14 electrons maximum. Okay, that's the only thing you need to know. And there is one thing that, and whenever I teach electronic configuration, I want my students to actually be able to write down, and this is this chart that I have provided you here. Okay, this is the way I actually fill up electrons. Okay, there is a very simple, straightforward way of filling up electrons in an atom. And if you do actually fill up electrons here based on these numbers, like maximum capacity S2, a P6, a D10, and an F14, if you actually put all those in this thread that I have shown here, all the way from 1s to 7p, and it's kind of raining from top left part of the page that you actually fill out. So you do 1s, then you do 2s, then you do 2p3s, 3p4s, 3d4p5s, then 4d5p6s, 4f5d 6p7s, 5f6d, and 7p, and you would actually reach out to this UUO, that is the last element, and the one with 118 electrons in it when you do 7p6. Okay, that's period 7 and a noble gas. Okay, so in order for you to actually do an electronic configuration, one tool is to have this. You need to be able to write this down, but how am I going to do this? Okay, so I'm going to show you what you do here to write down one of this, and then I'm going to start. So the way I do it, I just write down from 1 to 7. And then I start with the simplest orbital that I have, S, and add one orbital as I move on. So in the first layer, the period 1, I just have 1s, and the second one I have an s orbital and a p orbital. It's also 2p because it's period 2. Then I do s, p, and next one is d. So I'm adding 1 as I'm going forward, and these are actually third layer, s, p, d, f, and these are all 4, And as I move on to 5, I cannot add because I don't have any orbitals. So I keep doing F here for 5, P, D, F. That's 5, 5, 5. And now for 6, as I move on to my 6th layer, what I'm going to do is I'm going to decrease. So S, P, D, and I don't put F. So in contrast to the top part that I did, now I'm going to decrease. So 6P, 6D, and then 7S, 7P, no D. So you first increase, you keep constant on the 5, and then you keep decrease. And you will have this framework just as you see here. I'm going to use this as I'm going to write down electronic configurations, okay? There are 3 ways to put down the electronic configuration for any element in the periodic table, okay? Let's just go for first simple form of it, which called the full electronic configuration. The full electronic config. Let's just have this one move on the top so that we could see that this is going to be our guideline, okay, as we do this. I have chosen some simple molecules like boron and nitrogen. The only thing I need to know from the periodic table for a full electronic configuration is the sheer number of protons. So boron here has 5 protons, so 5 electrons. I do a 5 here. And nitrogen has 7 protons, so 7. Okay, these are, by the way, atomic number. If you ever wanted to show the proton, this number should go down, and the number of combined protons and neutrons should go on the top. If you have one number, that's the atomic mass or the number of protons, which actually determines the number of electrons. So I start from here, fill up maximum capacity on these, fill up maximum capacity on these rebels until I reach that. So 1s2, I need to move on. Again, the way I do go is rain from the left, okay? So 1s, then this, then this, then this, then this, then this, all the way to 7p, okay? So that's how I do it. Let's look here for boron. So 1s, then I move to this, and 2s. Now if I put 2s2, that would be 4 electrons. I move on, that's 2p. P contains 6 electrons, but I only need 1 more, so I don't need the maximum capacity for P. That's 2p1. For nitrogen, you know that it's 7 electrons, so 1s, 2s2, and 2p, so I need only 3. That's the full electronic configuration. There is also another way, and to do any other element, you just need this number. But for bigger number of electrons, like an example of the next example that I'm going to do is iodine 53. That number is very huge and you have to do a lot of work and it's kind of boring, okay? So there's this is called the full electronic. We could also do Nobel gas notification. Nobel gas notification is useful because we make use of the the noble gases. Now noble gases all have the configuration of P6 here, okay? And for the main elements, this is very important here. I'm going to point it out on this part, that how important this is to know. When we talk about electronic configuration, the first and second group are going to have the configuration S1, S2, okay? And then let's forget about these transition metals that kind of have D something in their configuration. But anything group 3 would have P1 configuration, anything group 4 a P2, a P3, a P5 for anything group, a P4 for anything group 6, a P5 for anything like fluorine, chlorine, or iodine, a P5 configuration, and anything on group 8 would have a P6 configuration. This P6 configuration is particularly important, and I'm going to use this marker to show you how important that is. So 2P, 3P, 4P, 5P, 6P, 7P. If I look at those, 1s is also important, but 1s is the configuration of the first noble gas here, helium. Okay, all those others, the 2p, 3p, 6, 4p6, 5p6, 6p6, 7p6, are all the way from neon, which is 2p6, to radon and last element in period 7, 6p6 and 7p6. So in the second mode of writing electronic configurations, I'm going to write down actually a noble gas and then continue from that to reach the number of electrons. This is called noble gas electronic config. Let's do that for iodine 53. To do this for iodine 53 with 53 electrons, there are two things to do. First, we have to realize which is the noble gas that I have to start, and after it, which kind of layers I have to fill out. This is what I need to do if I want to do that. Okay, so let's go back to our periodic table, and I'm going to find out my iodine in the periodic table. Iodine is right here, and if you see, iodine is this element out here, and I'm going to figure out what's the period for iodine in a grid-like manner and what's the group. From the group I can figure out actually its configuration. From the period I can figure out the number that precedes that configuration. So iodine is right here. I'm using my grid lock like this. So it's, as you could see, it's period 5, and also you could see that it's group 7. So this is the kind of grid lock that I've worked. Group 7 means it's a P5 configuration, and period 5 tells me that the last thing is a 5p5 in the configuration of an iodine. Okay, I also need another important thing about iodine, and that's to know what it is previous noble gas. So the previous noble gas before iodine, here is iodine 53. Let me get this out of my way, and I go back on a periodic table so everybody could see. This is iodine 53. If I move on all the way back to 37, there is no noble gas. As soon as I move on to 36, there is the krypton. Okay, krypton is a noble gas. There is, as you could see, 36 electron in it, and the symbol for it is Kr. So these are the three information that I need for my previous noble gas. That's a krypton that contains 36 electrons, and the third information is the period. If you look at the period for krypton, it's period 4. This is the period. Actually, I have written down that right beside that's period. It starts from here. So period 4 must have a configuration of 4p6. With this information now, I can go on to this and write down the configuration, electronic configuration of iodine 53. Okay, and that is to say iodine 53 has a krypton, and then I move. This is where I move after that when I do that, because when I do fill out all the way to 4p6, I have this krypton. That's the meaning of it. It means I have written down all the way to here, and I'm continuing from that 4p to reach my stop sign. This is the stop sign. So this is the starting point, and that is the stop sign. A starting point right after 4p6, and stop sign is a 5p5. So after 4p6, which is my krypton, that's a 5s. There's no stop sign on that. There's the 4d, there's no stop sign for that, and that's the 5p. Okay, and I do know that it's a 5p5, so I don't need to do maximum. The maximum for D is a 10 and the maximum for S is 2. Then I check back. Krypton just has 36 plus the 12 and 5. It is going to be exactly 53. Okay, that's how I figure out that my work is correct, so you can check it back. Let's move on to yet another example, doing the same strategy with a stop sign and starting point, and you could realize how we do it for other different elements. Let me do PB82. So for PB82, let's just get rid of that iodine that I put behind this, and I'll go to the PB. So for main elements, it's very easy. I just do the gridlock work. The period is the same number that I actually have, and the group actually is whatever the configuration of that group. PB is also a main element. It's group 4, as you could see, and if I put my gridlock on it, you could see it's also period 6. So this is PB82, and everybody could see it's 4, group 4, and then also, let me just move it to this place so everybody can see how it works. It's this period 6, so that's for 4, it's a P2 configuration. Remember, P1, P2 all the way to P6. P2 for its group 4, and 6 is the period. So this number is going to change if your element is not a main element. Okay, there's a rule for that, and we're going to go into that. But before that, let me finish doing PB, and then when I run to other D transition metals and also lanthanides and actinides, I would tell how to do with this one, and there are little more tricks about that to do. So for PB, that's 6p2, that is my stop sign. Where do I start? And I need those 3 information. I just move on to the previous noble gas before 82. Okay, so if I move all the way down to 55, there is no noble gas, and as soon as I move to xenon, xenon is a period 5, its symbol is Xe, 54 electrons, and its group, and it's period 5, so the configuration should be 5p6. Looked at the configuration of all noble gases are going to be p6. The p6 is not important, this number is important, so you look at the period, which is 5 in this example. And I'm going to start after 5p6 and go stop at 6p2. So 5p6 is going to be my xenon with 54 electrons, and I start after 5p and say 6f, no stop sign, 4f, no stop sign, 5d, no stop sign, let me get rid of this, and 6p. Okay, 6p is my stop sign, and I want to do 6p2. Okay, that's how I do it, and then 10 here, 14 here, 2 here. The 54, if you check, plus that 24 and that 4 makes up a 82. Okay, and that's how you do this. There's a 10 over here and a 4, so that's, my bad, a 8 over here and a 4, so that's 12, and that makes a 30 and an 82. Okay, so this way I have also checked back my work. Let me do yet another example. So let's try to do ZR zirconium 14, ZR 40, and 40 is a number for zirconium. My bad, is an element that has that is a transition metal. Okay, so that's also important because transition metals have a different work for we do a different work for transition metals, because transition metals, their group are not going to have the configuration as these main elements, and also the period is going to have a small difference. Let's just do the gridlock, and as I do the gridlock, I show you what's that difference. Zirconium, if you look, is period 5. This is zirconium here, as you could see, and that is the gridlock work. Okay, and for the gridlock, I just look at this number on the top as I start 1, 2, 3, 4, 5, all the way to 10. This is the maximum occupancy of D, so you know that it's a D2. Okay, so that's for the group, a D2. What D2 is it? Am I going to do 5 because 5 is the period? No, the rule tells me to do P minus 1. So if it's 5, I do 4D2. That's where I stop. Okay, where do I start? Well, that's simple. For D, there's also an exception. If you have a D4 configuration, there's some trick that you do after you write down the configuration. And if you also have a D9 configuration, that's also going to be the same rule, and we will talk about as we run into it. So D4 and D9, you have to do one extra step after you write down the electronic configuration to make sure it's the correct form. Okay, let's go on, continue on zirconium, which we find it's 4D2 that where we stop. Where do we start? Well, that's just like we did for other elements, and it's going to be the same for even the lanthanides and actinides, the same thing. So if I start with 4D with zirconium all the way to 37, there's no noble gas. As soon as I move to 36, that's the krypton. Krypton contains 36 electrons, and it is period 4, so I have to do 4p6. So I start after 4p6, that's my start sign, and I stop by this. So zirconium is going to be krypton, and that's after a 4p6, there's a 5s, a 4d, then I'm going to stop at 4d, so 5s and 4d, a 4d2, and 5s is maximum capacity, 4s is just 2. Krypton is 36 electrons, 36 plus the 4 makes a 40, so that's the correct work. Remember, for the transition metals, if there is a D4 configuration or a D9 configuration, there is one extra step. So for example, if I get an S2 D4, I have to change and rewrite it to S1 D5. Okay, because D is going to be maximum capacity for D is 10, and if it's half filled, it means it feels stable. Also, if it's an S2 D9, we're going to actually reject that just like you rejected this and rewrite it with borrowing one electron from S, because D would be now fully actually occupied, and it's preferable for D to actually be either half filled or completely filled. That makes the transition metal rather inactive or noble, sort of. Remember, when we talked about our periodic table, I told you that these elements right here are very unreactive. This is due to the fact that they have a D10 configuration. Okay, and some of them have even S0, which means there's no S electron in them. So they kind of had no metallic character to them. Let's do yet another example. I don't know if this is going to be the final. Let me just check. No, there are more to go. Let's do just selenium 34. I don't know how many more I could do, but I will manage my time. Selenium 34. Now selenium is group 6 and 34. I'm going to do the gridlock here for selenium. That is selenium right here. So it's period 4, as you could see. That's the main element, and it's group 6, as you could see. Group 6 means it's P4, and period 4 also means it's 4P4 that I have to stop. Then I take my gridlocks back, and I go back here. I'm going to go here, selenium, and then I go all the way. If you go all the way back from 34 to 20 to 19, you could see that there is no noble gas. As soon as you make to 18, that's argon. Argon is the noble gas in period 3, so 3p6 is what you need. So 3p6, it's argon, and it contains 80 electrons. So I start here after 3p6 and tell to myself this is my argon. Why do I put it in brackets? Again, that means that I have put down all those electrons until 3p6, and I follow after that with a 4s and a 3d and a 4p. 4p4 is where I have to stop. D if maximum 10, and S is 2. Let's just get rid of this to just not mingle out with what I have written down here. And my bad. 18 plus the 16 would be 34, I believe. 6 and 8. Yes, it's going to be 14. So that shows that I have done a correct job. Let's do yet another example. Scandium 21, SC21. And SC21 is also a transition metal. So as you could see, it's here. I put my grid log on it one more time. As you could see, it's period 4 and it's group D1. So it's D1. P minus 1 is the rule, so I do 4 minus 1. It's 3D1 where I stop. And if you go back from 21 all the way to 19 and then to 18, that's again 3p6 of argon with 18 electron configuration. And you also do argon. You start after 3p6, you do 4s and 3d. 3d1 is where you stop, and then 4s2. Just do these 3 closer to you, because it's better if you have a small space between them, so everybody understands that it's a different orbital. And also let's get rid of that to not mingle. So argon is 18 plus the 3 here, it's the 21 electron that you need. So that's the correct job for that. Let's also do one last example and should be able to wrap up this video with the example of a series of lanthanide. Thorium, let's see, thorium 90. Now if it's a lanthanide, the rule here changes to P minus 2, and there's one small trick, and that is for every lanthanide and actinide, because here when we talk about lanthanides and actinides, just put it down here so that I could speak easily about it. When we talk about lanthanide and actinide, we start here by doing a D, and actually a 5D1 and a 6D1 here for lanthanum and actinium, and we have that 1 electron in our D layer. Then we start putting electrons from 1 electron to 14 in the F orbital. Okay, so after we finish in our diagram here, we have to do account for that D1. Let's say I finish doing a lanthanide or an actinide or a lanthanide. 4F is lanthanide, 5F is actinide. When I do that, I continue one more step with either 5D1 or 6D1 to actually show that I do understand that before writing any lanthanide or actinide, there I put 1 electron in the D orbital of a lanthanum or an actinium, which are transition metal. We never go on to hafnium or rutherfordium to do the other D elements before we fill out all those, all those 14 electrons. So anytime you fill out a lanthanide or actinide, you have to do that.